In this video, we're going to look at some common small signal circuits and find their Thevenin resistances. This practice will be handy for finding amplifier parameters. I'm going to offer you the chance to work through these examples as I go through the videos, and doing so is great practice. The first small signal circuit we're going to look at is called the RE boosting small signal pattern. It's pictured above. You'll notice that we leave the far side of the current source floating, and that's because current sources have infinite differential impedance, so they perfectly hide impedances or voltages on the other side of them. Also, note that we're using a generic VC to describe the control voltage for our GM generator. Though in a BJT circuit, that VC is almost always going to be some VBE voltage. I'd like you to pause the video and try to find RTH. We solve this circuit by noticing that the emitter voltage is just R2 times the current flowing through R2, and that the current flowing through R2 is the current in R1 plus the current in the GM generator. We write this down over here, taking the shortcut by noting that the GM generator current is related to the R1 current because R1 times I in is equal to VC. We then note that VC is equal to I in times R1, and that our total input voltage is just VE here plus VC. So substituting these two expressions into this equation, and then dividing off R in, we get our expression for the Thevenin resistance, which is R1 plus GM times R1 plus 1 times R2. We saw exactly this result for the input resistance of the emitter follower, where R1 was R pi and R2 was a parallel combination of a bunch of stuff, including RE. The fact that R1 was R pi caused this GMR1 expression to be equal to beta, and since R2 had RE in it, we refer to this whole thing as RE boosting. This structure has the apparent effect of boosting the impedance of R2, and then that boosted impedance just sits in series with R1. We add R1 to this boosted R2 in our result. And that R2 boosting effect is because the GM generator supplies much of the current to R2 that's needed to set its voltage to the right level. That means the VIN source doesn't need to send as much current as if the GM generator weren't there. And the reduction in current coming from the VIN source makes R2 look like a much bigger resistance for a given voltage. This resistance boosting comes from a type of feedback. Raising VIN makes VC bigger, which makes IGM bigger, which makes VE go up, which in turn makes VC smaller. So the GM generator is kind of fighting to keep VC at the fixed level. Those feedback dynamics are interesting and actually have fairly deep links to control theory, but the main takeaway for now is that if you see a pattern that looks like a GM generator driving a resistor attached to one node of its control voltage, then the Thevenin resistance is given by this expression. The second small signal circuit we're going to look at is called the left-right circuit, and that name's going to seem weird for a bit because it's named after a circuit we'll see much later in the course. Pause the video and try to find RTH. We solve it by first noting that all of the current that flows through I in has to flow down through R left. It splits between the R right and GMVC branches, but merges back together down here. That means VC is equal to I in times R left. Then we write KCL at the top node of the circuit, observing that the current that flows in R right has to be the sum of the currents through the GM and I in. So this is the R right current is equal to I in plus the GM generator current. And then we rearrange that and sub in our expression for VC, in a few steps on this line and this line to finally reveal that RTH is equal to R right plus R left plus GM times R right times R left. So we haven't seen this pattern in a circuit yet, but it's coming up very soon. As a tantalizing hit, you could imagine that R right might be equal to RO in lots of BJT circuits, because RO is in parallel with the GM generator. And so with that hint in mind, be sure to look for this pattern in the output impedance of cascode amplifiers, which are coming up in the near future. This third term, which is the product of R right and R left, can be quite large. And so, as is the case with the RE booster, that boosted impedance comes from feedback. Increasing Vin ought to increase In. However, the total current seen by R right is reduced because the GM generator, increasing Vin ought to increase In. However, the total current that R right sees is much larger for a small increase in voltage because the GM generator produces some as well. The final small signal pattern we're going to look at is called the 1 over GM pattern. I've drawn it in a BJT way on the top, where we have sort of our hybrid pi model ghost of it here, and then in a cleaned up way on the bottom. These circuits are the same if you assume that the GM generator attaches to ground on the other side. And because we have no idea what's on the other side of a GM generator, it perfectly isolates the rest of the circuit, we're free to pick whatever we want to put there. So it happens to be convenient to say, let's imagine it's hooked to ground. I'd like you to pause the video and try to find RTH. In this video, we're applying a voltage source directly to the control resistor R1, right? Vc is just equal to Vin. And we note this when we write our KCL equation at the top node of the circuit. GM times Vin produces the amount of current that we are going to see in the circuit. Now, the GM generator is actually injecting current into this node, which is why we have a negative sign on our KCL. But Vn also causes Vc to become more negative as it increases. So we have a minus Vn terms here, and those negative signs cancel. These other currents are just Vn over resistances. We can arrange this expression to find that Vn over In, which is RTH, is 1 over the sum of some resistances, so it's a bunch of is 1 over the sum of a bunch of conductances, so it's GM plus 1 over R1 plus 1 over R2, and then all inverted. That is the same form as a parallel combination of resistors, so we rewrite this as R1 parallel R2 parallel 1 over GM. 1 over GM is usually quite small, so this equation is often approximated as just 1 over GM. We saw almost exactly this pattern in the emitter-follower circuit, though there was a minor difference in the emitter-follower result, where we added RS over beta to the 1 over GM term, and we'll explain that in the next video. In general, you should expect to see 1 over GM anytime you change a GM generator's control voltage by wiggling the node that the GM generator feeds. Making this more concrete for our class, you should expect to see 1 over GM anytime you wiggle an emitter. So, in summary, we saw 3 small signal patterns that appear in many BJT circuits. The RE boosting pattern, which has this Thevenin resistance, the left-right pattern, which has this Thevenin resistance, and the 1 over GM pattern, which has a Thevenin resistance of about 1 over GM.